Hey everyone, so with this video, I'm going to show you how to draw polypeptides. This is building off of your knowledge of being able to draw all the single amino acids. Okay, so first, when we talk about drawing polypeptides, let's just draw the easiest thing we can. Let's draw a dipeptide made from two glycine residues. Okay, so first let's draw two individual glycine residues separate. Again, by convention, we're always going to have the N-terminus go first. So here's my first glycine. And just so we recall what the stereochemistry looks like, remember if it's pointing that this alpha carbon, this carbon right here, remember that's the alpha carbon. If the alpha carbon is pointing down, then the side chain points back. If the alpha carbon is pointing up, then the side chain is coming out towards us. So here's glycine number 1, and here is glycine residue number 2. All right, so when these two peptides come together, we're going to lose a molecule of water. So this type of reaction, as it has been mentioned multiple times now in the class, is called a dehydration reaction. Okay. So when we form, so where is this water molecule we're going to lose? Well, we're going to form an amide bond, and just to sketch one out real quick, right? This is kind of what your amide bond is going to look like. So it has a carbonyl with a nitrogen right next to it. All right, that's our amide bond. All right, so we are going to essentially, you can see, so this carbonyl comes from the carboxylic acid moiety, and this NH is going to come from our N-terminal, so our amine on our amino acids. So we will lose this OH and one of the hydrogens coming off of the N-terminus of the very next residue. Okay, so what again will that look like when we draw this? How I practice drawing amino acids is I start with my N-terminus, and honestly, I just start drawing nice angled kinked lines. Right, these are all at about 120 degrees because that's going to be the angle we're going to be working with. All right, now this is probably too many, but I can always go back and erase. Actually, let me make sure I can draw them separately, so they on this tablet I can erase just each one line instead of the whole thing. Okay, so we start here. So I've got my N-terminus. So this N-terminus is this N-terminus here. Then next up, I'm going to have my alpha carbon. So this is my alpha carbon. It's pointing up, and I need to put my side chain on it. So this is hydrogen. Normally, if you're drawing glycine, you do not have to include the hydrogen. I'm just doing it so we can see how the stereochemistry plays out. Okay, so that's the alpha carbon there. Next up is going to be the carbonyl. All right, so there is my first glycine residue. Okay, next, so this next peak right here, that's going to become the nitrogen of the amide bond. So this is going to be an NH. So this is the N-terminus of the second residue. Then I've got another alpha carbon, right? So here's the next alpha carbon here. So we're pointed down, so we go backwards. Okay. Then I should have my C-terminus. Okay. Since this is just a dipeptide, I can erase those pieces because I'll have my C-terminus drawn over here. All right. So when we created this one dipeptide, right, there's my second glycine right there. When we took the two amino acids and brought them together to make a single chain, we lost one molecule of water and created one amide bond, right? So this is linking up the C-terminus of our first amino acid with the N-terminus of the second amino acid, okay? Let's try something a little more challenging. And I encourage you to try this with your name too. So my first name, lucky enough, all of the letters are single letter codes for the amino acid. So if you don't know it, my first name is Amanda. So A is ALA, right? M is methionine, A for ALA, N is asparagine, D is aspartic acid, and A is ALA. So let's make this 1, 2, 3, 4, 5, 6, this hexapeptide. This is going to be a hexapeptide. All right, so again, and remember, we're always going to have the N terminus on the left, and it's going to go to the C terminus over here. So to start, I am going to draw my N terminus, and let's draw it at pH 7, okay? At pH 7. Normally when I ask you to draw peptides, that's going to be at pH 7. So we start with our N terminus, and it's going to be protonated because the pKa of that is 9.5. So the pH is well below, therefore it's going to be protonated, so it'll have that positive charge on it. Okay. Then, like I said, I just come through and I start drawing kinks. My name's pretty long. I can always add more if I need to, but we'll start there. Okay, so it goes N terminus, and then I need alpha carbon, right? Alpha carbon's next. It's pointed up, so the side chain is going to come out at me, towards me. And alanine is a simple methyl group. I'm not going to write CH3 because that just starts to muck up my structure. So I'm just going to leave it there, right? We all understand, it's understood that if this is this wedge is coming out at us, there's a methyl hanging at the end of it. It's carbon. Then I'm going to have my C terminus. Okay. So there's my A. Remember, I'm dehydrating a water molecule, but next up is methionine. So this is going to link up with the N terminus of methionine. Okay. Methionine side chain is 2 methylene. So there's 1 methylene. Here's 2, a sulfur, and a methyl. So there's my methionine. And then I'll have my C terminus, my C terminal carbonyl left over from the dehydration reaction. All right, next up, ALA again. So we start with the N terminus of ALA. I've got this pointing up. So the methyl group for my alanine residue is going to be pointed out. And then I need to add my C terminal carbonyl from the C terminus of ALA. After that, we've got N for asparagine. So I need to put my N terminal residue there. It's pointing down, so we're going to go down and back. If we remember, asparagine has 1 methylene, 1 CH2, and then it has an amide coming off. All right, so there's my asparagine. Oh, wait, don't forget the C terminus. So we draw in that for the C terminus. Next up, let's go dark blue. Aspartic acid, D. So I need to start with my N terminus of the aspartic acid, up and out. So here's D. D is a methylene, so a CH2, right? A CH2, and then a carboxylic acid. Now the pKa of aspartic acid, if you recall, is 3.9. Remember, I want you to draw this at pH 7, so we're well above the pKa value. Therefore, it'll be a deprotonated side chain. Don't forget to always finish with your C terminus. Look, I needed more. See, I didn't even draw that much, but I just need an alanine. So I'd have my N terminus, my alpha carbon, and then the final stint. All right, so last amino acid in my name is alanine. So we start with the N terminus. We've got the alpha carbon here. It's pointing down, so we go backwards. And alanine is just a methyl group, so we're done with the side chain. Then we have to put in our C terminal. Remember, the C terminal has a pKa value of 2.3. We're at pH 7. We're well above the pKa value. Therefore, it will be deprotonated. So you'll see that negative charge on that carboxylic acid. So here's how this would be what my hexapeptide, my first name, looks like. Okay. again, you should, oh, well, let's see. So if you make a hexapeptide, how many water molecules did we lose? Every time you see an amide bond in the structure, that would indicate there was a loss of a water molecule. So here's one, right? We formed that one. Here's two. Here's the third. Here's the fourth. And here's the fifth. All right, so if we make a hexapeptide, we will lose 5 molecules of water. It'll always be that way. It'll always be kind of the number of peptides minus 1 will be the number of water molecules you'll lose in this dehydration reaction. Another thing to kind of mention right here, since we form these amide bonds, those amide bonds can have resonance. If you recall, I could draw a resonance structure for this amide bond. I'm just going to put R groups right here. Let me get a color here for some arrows where, oh, let's draw in our lone pairs. Bling. Okay, so I can draw a resonance structure for this amide bond where these electrons jump here and these electrons are going to kick up to the more electronegative oxygen. So what would that resonance structure look like? You would have R, O minus, 1, 2, 3, 4, 5, 6, double bond to the N, H plus, and an R group. Okay, so this form, again, you've got kind of an acid sitting right next to a base, so it's not really going to exist too long, but you can draw this resonance structure, and this is important in determining primary structure, well, really secondary structure, because the fact that you can make a double bond, let me go back to black, the fact you can make this double bond right here means that you no longer have free rotation around that nitrogen to alpha carbon bond. So it's kind of stuck. Therefore, if you look up here at all of these, well, if we highlight all of these amide bonds, there is no free rotation around any of these amide bonds. They're all kind of linear. They're stuck. I shouldn't say linear. They're all planar. Sorry, excuse me. They're planar, flat in the page. And that means that you can get what are called these phi and psi angles. Okay. In your book that talks about, it has a really great picture and it has what I call blue note cards because it's showing that the amide bond does not allow for free rotation. So essentially from the tip of this alpha carbon to this alpha carbon, you would see kind of that blue note card where that is all planar, what's in the plane there. And then from this alpha carbon to this alpha carbon, you would see another blue note card. Again, the blue note card refers back to the figure in your books. From this alpha carbon to this alpha carbon, you could see another blue note card. So essentially these polypeptides, the polypeptide chains, they're kind of stuck. Let me grab something super quick. So I've got these kind of two whiteboards here, whiteboards here. And so at each place, these are like my note cards. Okay. So where the two boards meet is the alpha carbons. Okay. And so you can only have rotation, or you think about my boards, you're limited to the rotation. And then the rotation, how far things can rotate is going to be actually really limited by steric interactions of all your side chains. So the bigger and bulkier, the less likely you're going to be able to rotate pretty far and get the amide bonds. So the amide bonds are essentially the plates, get the amide bonds interfering with the functional groups coming off your side chains. But you'd notice that sometimes in some previous exams, I'll ask you to draw a polypeptide and then draw where the blue note cards are, showing the areas of this chain that are planar. And this is what it's referring to. Okay, and these blue note cards exist because you can draw a resonance structure for that amide bond. All right, so this concludes drawing polypeptides. I really, again, encourage you to try your name, write out your name and just cross off any letters that aren't one of the 20 common amino acids. And then you can always go check yourself because you can look back and see what the side chains look like, right? And then you can also practice drawing these blue note cards. And it's pretty simple once you get that it's just from the alpha carbon to the next alpha carbon, and you make a box that boxes in this, somewhat resonance stabilized amide bond.